Okay, thanks very much, Alex, for the kind introduction. I've done something really clever today. I've managed to wear the same sweater and collared shirt combo as in the photo that you was used to advertise the talk, so there's no doubt that I am who I say I am. So usually I would start one of these off with a little, description of what McMaster is like and some pictures of the campus or something, but the crowd is almost 100% McMaster attendees, so I think we'll skip over that today, and I'll get straight into talking about what is solar reforming. Solar reforming is a class of photocatalytic technology. And so, like all photocatalysis, we're relying on light to stimulate the separation of an electron in a hole. This creates these two kind of high energy reactive species that can be used to drive oxidation and reduction separately. So our electrons can be forced onto substrate molecules, reducing them to form usually higher energy compounds, and our oxidation will gather electrons from substrates in our medium and use those as basically the fuel, and we're going to transfer those electrons, take them out of those donor substrates and transfer them onto acceptor substrates. And so this was first observed in this Japanese paper back in 1980, where they observed they're able to use glucose as their donor molecule, and to be able to basically source those electrons from glucose and push them onto free protons and water, creating hydrogen gas in the process. And so this class of reaction has kind of been dubbed as photoreforming, because it looks to the observer like we're transforming this organic substrate, glucose, into a different fuel product. We're transforming it into hydrogen. And then solar reforming is this same process. We're just stimulating it using sunlight energy as opposed to artificial light, which we typically use to talk about photoreforming. So photoreforming would be like UV or blue LED light. Solar reforming, we're just talking about using natural sunlight instead. Okay, so it's basically this applied form of photocatalysis, and we use these oxidation reduction half reactions. And on one half of the reaction, we're oxidizing these waste organics. We're trying to make use of these waste compounds that have no other intrinsic value, transforming those into useful chemicals on one half of the reaction. And on the other half, we're doing some other reduction reaction, either kind of the low-hanging fruit in this process is converting these free protons into hydrogen gas, or there have also been examples of converting carbon dioxide into higher order fuel compounds, or like carbon monoxide or methanol or something like that. So there are kind of two classes of this solar fuels type of reaction. We've got artificial photosynthesis, which is kind of mimicking what plants do at a kind of heterogeneous chemical scale. So there we're taking water, doing water splitting on the oxidation half of the reaction, and the reduction half of the reaction we're looking at using carbon dioxide as our carbon source, converting that into CO2 reduction product. And then solar reforming, what we're doing is we're replacing that water splitting reaction with this oxidation of these organic chemicals, this waste biomass or other waste materials. So a couple benefits of that are, first, we're able to make use of these low-value chemicals, as I said before. But the other thing is there's actually an energy benefit to doing this as well. Rather than trying to go through the really thermodynamically challenging process of splitting water, we can instead rely on combustion or oxidation of these substrate compounds and do this at a much lower thermodynamic level. So here we can kind of see the thermodynamics of the process. So if we're doing water splitting, we require that pretty high threshold, 237 kilojoules per mole, in order to initiate that process, whereas the Gibbs free energy for the overall reaction for oxidation of something like glucose gets us sometimes a slightly negative, but oftentimes just hovering around zero for our total Gibbs free energy. So there is the possibility of basically running these reactions or achieving higher production rates for our desired reduction product by replacing our kind of water splitting reaction with something that's a little bit more thermodynamically favorable. But this also does a couple of weird things to our metrics. So the traditional way of calculating the efficiency for these photocatalytic processes is that we look at the Gibbs free energy of the reaction that was required to form our fuel compound, right? And so if we take that in the case of water splitting, right, over here, we have this quite high Gibbs free energy that is required, and therefore we're storing that amount of energy, and that is kind of translating to our efficiency. But if we do the same thing for our solar reforming process, we end up with this really weird concept of having a near zero efficiency because the Gibbs free energy that is required to form that fuel compound is suddenly so much lower. So we're trying to think of ways that we can kind of more accurately represent this. And the reason that happens is because we're really relying on nature or some other process to take our carbon dioxide and hydrogen all the way to this biomass that can then be oxidized to produce our fuel product. So a lot of this work is done for us already, and we're just kind of capitalizing on this last step here. But so now the question is, like, how are we supposed to properly represent that efficiency? Should we, instead of looking at the energy that was required to produce this fuel compound, rely on the energy that is embodied within the fuel compound and use that as our representation of the energy that we can get out of the process? Maybe, but it's also not really a true representation of the energy that we're storing through this process. So there's kind of some open questions about how we track the efficiency of these processes here. Okay, but overall, why do we care? So our current chemicals economy looks something like this. We start out with fossil fuels. We do something to those fossil fuels, refine them into a form that can be used to make these useful products, and manufacture them into products that go into the economy. They're used, and then on disposed at end of life, they go to the landfill, right? So we're basically a very efficient means of taking oil out of the ground and eventually turning it into landfill at some point. And this is quite a lot of our oil that goes into this. So the chemicals production industry comprises about 30% of global energy use, and it comprises about 14% of global oil demand. About half of that is used to produce the energy that is required for these processes, and about half of that oil is used directly as feedstock chemicals in order to make these products that eventually end up in landfill. So, you know, there's been a lot of discussion over the past decade about kind of introducing this idea of a circular economy, and that's something that perhaps solar reforming can play a role in. And so then some other statistics. So this is overall contributing to about 2 gigatons of annual waste production, and most of that waste ends up in landfill. And a good portion of that waste is plastic materials as well, which are persistent. Okay, and maybe a kind of a very optimistic future proposes that we have a circular chemicals industry, and maybe the solar reforming process has a role to play in a future circular economy as well. So in this case, we're sourcing, instead of fossil fuels, we're sourcing biomass, and perhaps we're also sourcing kind of these waste materials from end of life, putting them back into the process here, doing some kind of pre-treatment, and then doing this kind of sunlight-driven solar reforming to make these useful feedstock chemicals that can be used in these manufacturing processes. And the two main classes of solar reforming are kind of direct photocatalysis. So this means we basically got some kind of semiconductor material. It absorbs light, and then it's usually coupled with some co-catalysts that will allow us to do specific oxidation and reduction reactions. And these usually happen on the same kind of particle material, and there's no separation of our oxidation reduction reactions beyond that. They're both happening on the surface of this single catalyst material. And then the other main category of solar reforming devices are these photoelectrocatalytic devices or photoelectrochemical devices, and these operate very similarly to an electrocatalytic reactor, where we have, you know, a separated anode and cathode, except that one of those anode or cathode is replaced with a light responsive material, and so that can provide some or all of the bias for the process. And so in this case, we have kind of this divided, separated oxidation and reduction reactions. But I will primarily be focusing today, or actually entirely focusing, on photocatalyst materials, so just these direct photocatalyst materials. And the part that I'm going to be focusing on the most is going to be on catalyst reuse. So catalyst reuse is something that's pretty critical for economical deployment of these materials for solar reforming. So there was a study that was done in 2021 by actually the group that I had joined at the University of Cambridge, and they did this analysis of solar reforming materials, and they found that these various factors were the kind of most important in determining whether this technology would be economically viable or not. And there were two factors that kind of bridge this this enormous break in the graph here that push our production costs up to kind of unreasonable numbers, right? And those two were catalyst reuse. So basically, if we need to deploy a new catalyst material every time we want to run this reaction, it's going to make this process just too costly and inefficient in order to run. And the other one is this sodium hydroxide reuse, and this has to do with preparing our substrate material to be accessible for the solar reforming reaction. So I'll return to that very briefly at the end of the presentation, but I'm mostly going to focus on this catalyst reuse strategies. And the catalyst reuse strategy that has been deployed most widely up until this point has been just depositing these photocatalyst materials onto solid panel type materials. So for example, we'll start with a glass substrate, treat that somehow, deposit our powder photocatalysts, and we end up with a panel of material. And that's what was done in this research group as well. Shortly after publishing this paper, they came out with this paper on this carbon nitride-based photocatalyst. They made a panel by depositing this onto glass substrate there, and then they will flow their substrate solution containing these oxidizable waste molecules across that panel. There are some downsides to this, however. Our mass transfer is a little bit more limited, we're also usually placing this light active material below the substrate solution. So this means that we need to work with transparent solutions in order to run those reactions as efficiently as possible. So something that I'd proposed and something I'd worked on previously at the University of Waterloo. So Alex mentioned earlier, I had founded this startup company, H2 Nano, and we had focused on these water treatment technologies using floating photocatalyst materials. And so when I went to Cambridge, we discussed with Erwin there about, well, maybe we can make these kind of floating photocatalyst materials for solar reforming as well. And floating introduces a few key benefits to this process. So the first being light harvesting. So whenever we're dealing with solar radiation, it's always coming from the top of our vessel, coming from the sun. And so it makes sense to localize our catalyst materials at the air-water interface, right? This is where the sun is going to be touching our solution, and so that's where it makes sense to put the material that is going to be gathering and using that light. The second thing is it's beneficial for product separation. So if we are making gaseous products, i.e. hydrogen, that's kind of our lowest hanging fruit, or making syngas, carbon monoxide and hydrogen together from carbon dioxide, we don't necessarily want to produce that product in kind of the bulk of our liquid suspension and then rely on diffusion and or stirring to kind of bring that to the surface. It kind of makes sense to produce it at that surface and allow for kind of that rapid product separation. And there has been a couple of studies out of Korea in recent years that have shown that it is a significant benefit to the closer you can localize your catalyst to the air-water interface, the much faster your production rates can be. And then finally, the last benefit is for catalyst recovery. If we want to remove our treated substrate, or once our waste material has been fully oxidized or expended, we want to discard that. We want to retain the catalyst, and if we're deploying it in kind of this slurry method with these floating powder systems, we have this natural built-in gravimetric separation, and we can rely on that to recover and reuse our catalyst. So how did we make these? So we're using carbon nitride, which is this low-cost semiconductor material, can be produced from the pyrolysis of melamine or basically any ammonia-rich carbon compound. It's also being made out of urea, for example. But we would calcine this and then grind it up into these kind of smaller microparticles, and we end up with this powder material that's kind of got a density of around 2 grams per centimeter cubed. But of course, that is too dense to float, and so we need to reduce that density somehow. And the strategy we took to do this was we used these hollow glass microspheres. They're a filler material that are often used in things like concrete or basically anytime you need to lower the density of a composite, basically. And so we just added this into the synthesis process, crush it up in the same way, and you can see on the micrographs here, we end up with these hollow glass microspheres that are kind of trapped in an overall cake of this carbon nitride material, and this has varying density from less than 1 all the way up to chunks of material that have no filler in them at all, around 2 grams per centimeter cubed, and then we'll separate those fractions apart. So here we've got an example of this floating material. So it's stirred in our aqueous suspension at 0 minutes, and then after 2 minutes, you start to see visible separation of that floating layer migrating to the top. After 10 minutes, we have almost complete separation. And so we'll do this with kind of the raw material that comes out of that synthesis process, and we can fractionate it into fractions of different density. And I'll talk about why that might be a little bit more important later. We can also control the overall carbon nitride content of the composite by just varying the melamine to glass bubble ratio. So when we use a very low ratio of melamine to glass bubbles, we get kind of these thin layers of carbon nitride that are coated around those glass spheres. And as we increase the content of melamine, we get more and more carbon nitride, eventually forming these kind of masses of carbon nitride with the embedded glass microspheres rather than the other way around. Okay, and then we applied these carbon nitride composites for the solar reforming process. And so we found that as we increase the content of carbon nitride, we also increase the production rate of our hydrogen gas doing this photoreforming reaction. And we found that by using different types of co-catalysts, either platinum, shown in blue here, or nickel phosphide, shown in orange, we can achieve hydrogen production at kind of varying kind of efficiencies over multiple cycles. So we found that by using the standard platinum co-catalyst, it's a very robust material, it's very inert, right? It doesn't change very much from reaction to reaction. We're able to retain most of our activity over the cycle, whereas when we end up using the nickel phosphide co-catalyst, it oxidizes over time and its activity decreases. So not exactly what we were hoping to see here. It'd be really nice to be able to use this kind of transition metal catalyst material, lower cost, more environmentally friendly. But unfortunately, it's just not as robust as the platinum co-catalyst is. And so that's kind of a theme of what we're going after for these catalyst composites. We want to make sure that they're durable and can be reused a sufficient number of times in order to improve the economics of this process overall. We're also able to realize another one of those benefits of using the floating material. So we applied this composite in a turbid waste environment. So you can see this pretty cloudy substrate solution here. And when we basically apply the floating composite material, you can see over here on the left, we're able to get hydrogen production activity recorded versus if we use the non-floating catalyst material, not very surprisingly, sinks down to the bottom of our solution, and it doesn't gather any light and is unable to produce hydrogen in those cases. And then we basically did some controls for that as well, but just lending some credence to the idea that this floating composite allows us to do treatment or solar reforming in kind of substrate conditions where it wouldn't usually be possible. Okay. Okay, and then talking about the kind of stability of these composites. So the activity decrease that we observe in these materials, I'll just go back a couple slides here just to show this again. Okay, so we have this kind of decline in activity for our nickel phosphide based material, and that's due to degradation of the co-catalyst. And so that's like not a, that's like a materials change, a chemical change that is affecting the viability of that catalyst composite. But in this example here, there's nothing that shows our activity of the composite itself on like a mass normalized basis is changing. We think the reason that we're getting lower and lower activity over the course of these runs is because we are actually losing the composite itself, right? These glass microspheres are kind of fragile. As they break, we get some of this material settling out, and it's no longer usable as a kind of recoverable photocatalyst material. So it's the purpose of this slide down here is just to show that the actual activity of this material isn't changing after use on a mass normalized basis. We're still able to get the same or perhaps even better activity from that carbon nitride platinum composite. The reason that our overall activity is declining in our batch reactor is because we're losing material. cycle after cycle. So we need a better way of kind of maintaining that activity. Okay. Another one of the pieces of the puzzle of solar reforming is how can we do better product selectivity? So kind of the low-hanging fruit in this reaction is doing this kind of free protons to hydrogen gas production using these waste substrates as kind of an electron source. But the real value of solar reforming would be if we can take these waste molecules, convert them to something that is of higher value, right? So then we're producing a useful fuel product on the reduction half of the reaction, and we're producing a useful chemical product on the oxidation half of the reaction. And that's something that we were able to do during my postdoc as well. So here we've got titanium dioxide as our light absorber, so a slightly different material from the carbon nitride that we're using earlier. And we've coupled this with an enzyme, formate dehydrogenase. And so this allows us to catalyze the conversion of carbon dioxide to formate. And we're actually able to do the same product generation on the oxidation half of the reaction by doing direct oxidation of glucose over the TiO2, producing this arabinose and formate here as well. So this is quite interesting because we're able to do the same product generation on both halves of the reaction. And we were able to demonstrate that using kind of radio labeling. So when we were producing our products using just C12, so just standard glucose and carbon dioxide, we just get this single NMR peak here. And once we introduce radio-labeled carbon into our CO2, we start to get the peak splitting. And then once we use both radio-labeled carbon dioxide and glucose, we only get the C13 formate product. So that shows us that we're actually producing the same product from both halves of the reaction and not just selectively from one half or the other. So basically, the takeaway message is that we can change the selectivity of our reaction or target specific product by incorporating different types of co-catalyst materials, right? So here we're able to use an enzyme co-catalyst to change the overall reaction that we're doing, same type of light absorber. And of course, we, since the theme of this talk is on kind of floating a recoverable photocatalyst for this purpose, we took this system and we applied it onto this hollow glass microsphere support the same way as we did for our floating carbon nitride system. So we've anchored the TiO2 onto these hollow glass microspheres using a sort of cement, and then on top of that we're able to anchor the formate dehydrogenase, and then that's able to accept electrons from the TiO2 light absorber. And this allowed us to do kind of this floating system where we're able to do so we've got these kind of two layers here. We've got this layer of this floating photocatalyst, and this is catalyzing our formate CO2 to formate transition through this enzyme. And then over here we've got this kind of bulk solution where we've got our solid biomass substrate. So here we're using cellulose, and in that solution we've also got cellulase to do enzymatic depolymerization of that cellulose into glucose, and then that glucose is used as the substrate for the photocatalytic reaction. So we've kind of, by integrating this floating approach, we're able to do these two reactions simultaneously, depolymerization of cellulose in the bulk, and at the surface we're able to do our production of formate through both halves of the reaction. Okay. And something that we've done very recently, so we just published a paper November on something that I had started on working on just before I had left my postdoc. And that is using the different, or the tunable density of these floating composites in order to do kind of biphasic reactions that allow us to do kind of different product separation or catalyze reactions that require reagents that are present in different phases. So to date, most of the work that we see in the literature is on using these dispersed photocatalyst powders, and they're catalyzing oxidation reduction reactions together. Or these floating photocatalyst powders, where we're doing kind of an oxidation reaction in the bulk, and then our reduction is producing this gas product, and we're separating that to the gaseous phase. But what we thought is, well, there's no reason why we can't control the density and stick our catalyst layer at the interface between two different liquid layers of different density. So what we did here is we took our organic phase. We said we're going to do an oxidation reaction in our organic phase and produce a useful product here. We're going to do a different reduction reaction in the aqueous phase, produce a different useful product over here. And we're going to have this floating catalyst layer sitting at the interface between these two phases so that we can do both of these reactions simultaneously and allow that kind of inherent product separation. Okay, so here's a photograph of what it looks like. Just find my mouse here. So we've got our floating photocatalyst powder here, sitting at the boundary between our organic phase and our aqueous phase here. In this case, we looked at a couple of different reactions. The first is this entire phase is butanol, and we do a conversion of this butanol to butanal, so just doing an oxidation reaction there. And it's coupled with the reduction of water or oxygen, reduction of oxygen to form hydrogen peroxide in the aqueous phase. Right. And so then just a kind of a schematic representation of this, and then we looked at different ways of making this photocatalyst layer. And instead of relying on these hollow-glass microspheres, as we had used in previous papers, we looked at using a plastic support material. So now we can upcycle these addition polymers into as kind of these low-density support for our photocatalytic materials, and we can use their different densities in order to kind of tune the overall density of our catalyst layer to target it to float in between these two different phases here. And so a schematic of the reaction that we're catalyzing here. And so when we run this reaction in batch, what we see happening is our butanol product, so our oxidation product, shown in orange here, kind of linearly increases over time. We're able to continuously get butanol production, but the concentration of our reduction product, the hydrogen peroxide, kind of plateaus at a certain point here. And the reason for that happening is we're actually getting photocatalytic decomposition of our product over the carbon nitride once it reaches a certain concentration. And so in order to avoid that, we looked at transitioning from kind of these batch reactor photocatalytic processes and incorporated this kind of flow reaction technique. So here we're continuously cycling our aqueous phase and basically moving our product at a certain concentration out of this reactor, which allows us to continue producing hydrogen peroxide without having it decompose over the photocatalytic material. And so you can see here, this is the kind of concentration of our extracted hydrogen peroxide. It eventually plateaus at a certain point, but we're still able to extract those molecules. And so these dashed lines here represent the total amount of product that we'd be able to get out of a batch reaction, and we're able to exceed that theoretical maximum by moving over to this kind of continuous production technique. Okay, and one of the things I've talked about continuously is kind of the need for these more durable catalyst materials. So here is some of the results from that carbon nitride paper that I saw earlier, that I showed earlier. So we've got kind of this decrease in activity, which I think is due to loss of material over time. And we see a very similar behavior, or actually pretty, substantially worse in our carbon nitride polypropylene or our plastic-based materials, where run over run, we get a significant decrease in the activity of the material just due to shedding of our catalyst material from that floating support. Okay, so basically these hollow glass microspheres have low durability. They break pretty easily. The carbon nitride can shed off of this plastic material. We can reduce this shedding somewhat by adding an annealing step to our production process. So if we anneal the carbon nitride, we're able to reduce that shedding quite substantially, but we still get this kind of decrease over time. We're losing some activity. And so in order to meet this high standard of reusability, we still need to significantly improve the durability of these composites. And that's something that we're working on in the lab here at McMaster. So this is how we make these kind of plastic-based photocatalyst composites. Start with these pellets of our polymer, freeze them, micronize them into these kind of small microparticles, and then mix them with our catalyst material at a high enough temperature that we're approaching the melting point of the plastic, and we're just relying on that kind of a physical kind of a softening of the plastic material and embedding our photocatalyst into that surface. And so here's some micrographs we took at McMaster. So this is our pristine catalyst surface, and then this is our pristine polymer surface. And then after we coat it with our catalyst material, you can see all of the kind of carbon nitride components that are stuck to the surface there. And we've found that kind of by adjusting the type of plastic that we're using, the type of photocatalyst that we're using, and the processing conditions, we can achieve varying levels of photocatalytic activity and varying levels of durability. So something that one of my grad students is working on has been kind of varying the processing conditions for these different catalyst composites. So we can see when we prepare these catalyst composites at relatively low melting point, or relatively low temperatures, kind of below or very close to the melting point of the plastic, we're able to get pretty high activity, so very rapid. This is a dye degradation assay used as kind of a stand-in for our photo reforming process. We're able to get pretty high activities, and our activities decrease the higher the temperatures we use, presumably because we're melting the plastic more fully and more of our photocatalyst material is embedded into those plastics. But we also have this situation where we want to achieve this high durability on application. So you can see that at the lowest temperature, which gave us kind of the highest overall photocatalytic activity, if we subject this composite to this accelerated aging test, either we stir it at a very high rate or we sonicate it, we're able to kind of shed that photocatalyst off of the surface of the material, and our activity decreases quite substantially. Whereas if we use a material that is prepared at this higher temperature, so getting closer to the melting point, or more solidly embedding that material into the plastic support, we get a much lower change in activity after we subject it to these accelerated aging tests. So that's where we're going from here, is we're doing these kind of reusability tests. So in all of the previous examples I've shown you, every time we do these reusability tests, we try to disturb the solution as little as possible in order to prevent any abrasion of our material, try to preserve the photocatalyst later on the surface. But what we're doing in the lab now is we're subjecting these catalysts to these accelerating aging tests after every single cycle. So after every cycle, we gather the catalyst, we either stir it at a high rate or we sonicate it in order to provide kind of a really harsh condition to try as best we can to break the material off of that surface. And so we can see in both our dye degradation assays and in our kind of photocatalytic hydrogen production tests, after kind of this first test here, we get a little bit of loss of material, but then after that point, we're able to maintain a pretty consistent production rate and or dye degradation rate. Okay, and then I'll just end off with kind of a couple thoughts about kind of the bigger picture. So why are we interested in floating and solar fuels in any case? So floating systems seem like an ideal platform in which to investigate these solar fuels. So over the past decade, and really in the past 5 years, there has been a huge increase in the number of floating photovoltaic systems that have been installed for electricity generation. And usually these are coupled with things like hydroelectric reservoirs, right, with a dam, so you've already got your electricity infrastructure there, and you're able to couple this kind of floating photovoltaic array to that existing energy transfer infrastructure, and it also has the added benefit of providing shade to like reduce reservoir evaporation, etc. But we can't do this everywhere, right? Only in locations where we've got access to an electricity grid and can offload that generated power. Solar fuels, on the other hand, produce this inherently transportable, inherently storable chemical fuel material. And almost every solar fuel process requires water as a reagent in this. So for example, anytime we're making hydrogen, we're relying on those free protons in water. So it almost makes sense that we should be installing these kind of theoretical solar fuel production systems close to existing bodies of water. And so we've got a couple of theoretical kind of plant designs, one that is relying on photothermal water splitting to produce hydrogen gas over open water here, and then another one that is coupled with kind of an industrial water source that can use the waste organics that might be present in that organic-rich wastewater in order to produce useful oxidation products, and then maybe we're also using carbon dioxide to produce a useful fuel product on the other half of the reaction there. In recent years, there have been a significant increase in the number of floating kind of materials that have been that we're seeing in the literature. So these, so of course, this is an example from my paper earlier. This is an example from artificial leaf, which is a photoelectrochemical device designed with this kind of gas collection baggie here that provides it with its own buoyancy. So it's like a prototype for these kind of floating solar fuel devices. This is a floating photothermal water vapor splitting. So this may be useful, for example, when we're dealing with briny conditions that might interfere with our kind of water oxidation process. Instead, we rely on solar heat that is not usually used in the photocatalytic process to evaporate that water, produce water that is free of these salt molecules that might induce these parasitic reactions, and allows us to do water splitting over even high salt conditions. And then this is an example from 2025, this kind of TiO2 hydrogel system out of a group in Korea, where they produced these scalable hydrogel sheets, and we're able to scale this up to about 1 meter squared in dimension. So this is some exciting developments in the world of floating photocatalysis. And in fact, the largest example of floating photocatalyst application has been right here in Canada. So I mentioned earlier in the talk about this company that we co-founded back in 2015. So the original idea behind that company was we're going to produce these floating photocatalysts that are going to passively sit on top of these oil sands process water reservoirs that contain these toxic organic compounds, and we're going to, over time, allow that kind of passive photocatalytic reaction to detoxify the water. And so over the past 10 years, we've been going from lab scale to slightly larger pilot scale, and over this past summer, H2 Nano did a 100 meter cubed per day treatment pilot, and we're able to demonstrate that we're able to detoxify this water using this floating photocatalytic compound. So here we've got kind of this floating powder photocatalyst material. It's contained on top of one of these wastewater lagoons, doing this passive detoxification. But we can also speed up the process by introducing them into these raceway ponds where we provide some agitation through some low energy mixing and circulation of the wastewater. Okay. So the, I guess, overall takeaway is that the utility of these floating photocatalysts is already viable for water treatment processes. And in my mind, it makes sense to couple these existing water treatment processes with a production of a high-value product. So not only are we kind of getting rid of those toxic compounds, making that water viable for release, but we may also be able to produce a useful fuel or chemical product from that as well. And so that's where I kind of see this going. I'm hoping that I can couple these kind of solar reforming materials to these large volumes of aqueous waste. Although one of the remaining parts of the puzzle here is how we make these waste sources available for solar reforming. So when we're typically dealing with plastics, the easiest plastics for us to target are these condensation polymers that can be hydrolyzed to produce these ethylene glycol, which is an easily oxidizable substrate here. But of course, this isn't possible for all plastics, and not even possible for all biomass. Anybody who's worked with lignocellulose knows how difficult that can be to break down. So another one of the things that we're going to be working on here at McMaster in the next couple of years is targeting this NaOH reuse problem. So this is the other part of the puzzle that needs to be solved in order for this process to be commercially viable. So we're looking at ways that we can use solar heat in order to depolymerize these compounds as well. But hopefully more on that the next time you hear from me. Okay, and so with that, bring it to a close. So thanks very much to, of course, my previous group at Cambridge, where a lot of the work that I talked about today was done. Thanks to my current graduate students, and then also to Youngie Kim for use of his GC system, H2 Nano, for supplying the images there. And to you for listening to my talk. So, thanks very much. Okay.
You have this mixture of hydrogen and oxygen. If it's just hydrogen, fine, it'll work.
Yeah.
But this is ready to detonate at the slightest defect.
Right. Yeah, it's a.
But it seems to be an inherent problem with the concept of photocatalyst, that the separation isn't built in. So in the case where you had sort of other byproducts, the problem solves itself maybe, but here.
Yeah, so this isn't the case that we're doing direct water splitting and producing oxygen as one of the products. Yeah, for sure. I mean, the other option is, the other option is that after we do the separation, we don't compress the oxygen, we just release it. I don't know. This is a, concept. It's not something that we have explored in the lab. This is just us trying to say, maybe this is a potential application of this technology.
I'm really curious about this. It seems to me the efficiency of the process should be related to sort of the number of photons per square nanometer. So the floating glass beads with TiO2, that makes perfect sense. You get lots of surface area, they're bubbling around. But if you look earlier on the talk where you have this other stuff, I mean, they seem like rather large particles, a lot of which will not be accessible to light. Did I get it right or wrong?
Yeah, for sure. So obviously we want to increase the surface area of our catalyst. It also, like when we're using those hollow glass microspheres, there is some ability to capture any light that initially passes through that material. We've got like reflection within those systems. That is a nice system to work with. It's just that inherent fragile nature of the material, right? So we've got to try and balance that durability of the material and ability to kind of capture and reuse it with its inherent ability to capture the photons.
Polypropylene beads or something like that. I mean, the equivalent would be a bit more resilient, but very high surface area.
For sure, yeah. And then we also have to match the the size of the support material with the density of the material and the thickness of that photocatalyst layer that is around there as well. So there are kind of a lot of knobs that have to be tuned in order to get the exact right material, the optimal material. Yeah.
Thank you for your talk. When you show the delta G values more or less at the beginning, all of them appears to be for the processes you're looking are negative. What it means that it looks like you're oxidizing your starting material and getting the products which are more on the downside in energy. Is it my understanding?
Yes, I think so. So usually when we look at those efficiency calculations, that energy is what's required to kind of do that oxidation reaction. We're looking at that as the amount of energy that we're storing in the process in order to do those efficiency calculations. When we're dealing with the oxidation of those waste substrates, it's this downstream process. So either we have kind of a zero efficiency or we get this negative efficiency, which doesn't really make sense, right?
Essentially, it looks like you're oxidizing your fuel.
Yeah.
Okay, and using solar energy, which is actually my next question. Essentially, the solar, when you say you use solar energy, essentially you're going up in delta G as water splitting, classical one, but you're going down in delta G. So what's the role really of the solar energy?
Yeah, so the solar energy is used for that transformation of that existing organic compound and just converting it into something that is more readily useful as like a fuel material or as maybe a higher value organic compound that could be sold. So we're just using it to do that kind of small step, and then we're capturing whatever hydrogen is produced in that, and that's our desired product, right? So it is in a way like we are kind of in some cases losing a small amount of energy by oxidizing that existing waste product to the hydrogen. But the difference is that we have a low value organic compound that we're starting with, and then we're getting something that has value at the end of that. Does that kind of make sense?
It makes sense. I mean, so the sugars do not make sense, but if you have organic waste in the whatever sewage, that makes sense.
Yeah.
I would imagine if you're using general waste materials, there's a real problem with your feedstock being of very variable character. Is there something intrinsic about the approach that you're using that can be desensitized to that, or tricks that you can use? You did mention early on that in general you have to condition your raw materials.
Right. Yeah, so substrate selection is pretty important. Even within that example of plastic I used, like the ethylene glycol is readily oxidizable, but that terephthalic acid is not, right? And so then, so right off the bat, we've got only half of our material that can be easily converted into something a little bit more useful. So yes, when we're dealing with mixed waste streams, it becomes a lot more complicated. And even not just materials that can't be easily oxidizable, we also have materials that might foul the surface of the catalyst or poison the catalyst or whatever. And so actually one of the things, growing pains we went through with H2 Nano was working with a whole lot of different industrial waste streams and trying to find ones that worked for the process. And so yeah, that's something that I think we're going to have to look into targeting with our pre-treatment processes. We're going to start with kind of as pure substrate streams as possible, then work towards mixed wastes and kind of try to figure out where the problems lie.
I see you are brave enough to do some work with lignin.
Yeah.
Many of us have suffered that. Canada produces a lot of black liquor already at very high pH. That might be a good substrate to look at.
Yeah, definitely. That's on our radar. And in fact, one of the things that we looked at here, so like I talked about this in terms of the butanol and butanal system, but in fact, in this graph here, this 1A, B, and C, that's viraldehyde, syringaldehyde, and vanillin. So these are kind of lignin fractionated compounds. And so we were able to do some oxidation of kind of these lignin derivatives as the oxidation substrate for this reaction here. So yeah, definitely something that's on our radar, and hoping to be able to use that as a potential source of biomass for the process.
Any other questions? Okay, please join me in thanking Stuart and Melissa.